All right, so let's take a look at that. All right, so here's a surface, and I'm showing this point here. Let's see, does the red show up? Try a different color. Maybe green. I don't know. What's better, green or red?
Red.
Red's better, but yellow, no. Red seems to be the best, so we'll go with red. Okay, so here's this multivariable function represented here by a surface in R3, and I've got this red point, and I want you to, what can you say about the partial with respect to x and the partial with respect to y and the gradient vector? What can you say about the partial with respect to x, the partial with respect to y, and the gradient vector? So here's the x-axis pointing at you right now, and y is to the right. So what about the partial with respect to x? Can you make any observations or things to say about that? What's that? The partial with respect to x, what do you think? Someone says negative. Who says negative? How come, Ryan?
Because if you come further out of the screen, the z of the function is going to go down.
Yeah, well said. If you come a little bit out of the screen, z is going to head down. That means our rate of change in the x direction is negative. All right, what about partial with respect to y? Yeah, because if you go a little bit to the right, you're going to be heading up. Okay, what about the gradient vector? So if I asked you to tell me something about the gradient vector at this point, could you tell me anything about the gradient vector? Yeah. Negative x and positive y. So it would be like in what quadrant would its direction be? If we're thinking about the R2 plane and directions, what direction would the gradient be? Be pointing pointing into the second quadrant. Second. Because x would be negative, y would be positive, so you'd be pointing. The gradient would point back, because the gradient is the direction. What's the gradient the direction of? Greatest positive rate of change, right? So that would be pointing into the second quadrant, right? Okay, so let's talk more about, let's take that a step further here. Not that one. So let's talk about the second order partial derivatives. I think this has popped up in web work, but we haven't really talked about it yet. So in web work, I think you're just basically finding the values of the second order partial derivatives, and I kind of left that to you to figure out. You just take your first order partial derivative and you either differentiate it again with respect to x or with respect to y. Okay, so then you end up with 4 second order partial derivatives: fxx, fxy, fyx, and fyy. So what would fxx, or the partial of x, the derivative of the partial of x with respect to x, what would that reveal if you remember back to your Calc 1 stuff? What would that reveal about our function? Yeah. Okay, so yes, that's kind of the graphical result. But what is that about? What is concavity about? Yeah.
The change of the change.
Yeah, so it's like the rate of change of the rate of change, right? So let's put it this way: how the rate of change of z with respect to x is changing with respect to x. So again, we're going to make a small change in x, or let's let you do that. So can you describe the meaning? So going back to our meaning of rate of change, so a partial second order partial derivative is just its own rate of change. And so we think about how we describe rate of change. Could you describe the meaning of fxx with a sentence using our meaning of simply rate of change? Because a second order partial derivative is, on its own right, it is a rate of change. So can you describe it? So why don't you actually get a partner and see if you can talk that out. Okay, any volunteer? Did you talk it out? This is kind of a tongue twister to say this. Anyone want to give it a shot? Yeah, Jonas.
So at the point xy,
Okay.
for a small change in x,
For a small change in x, okay.
the rate of change of z with respect to x will increase by ffx times the small change in x.
Okay, yeah, right. So given a small change in x, what? The first partial with respect to x will change by fxx times as much as your change in x. So given any small change in x, the change in your rate of change with respect to x, or your partial with respect to x, will be that fxx times as much as dx. Okay, so if fxx is greater than 0, what can you conclude? What can you conclude if the second partial with respect to x, and let's talk about rate of change, not the graph, right? So what's happening with rate of change if fxx is greater than 0? What's that, Harrison? He wants the rate of change will be increasing. The first partial with respect to x will be increasing.
It's increasing at an increasing rate or decreasing at a decreasing rate?
So that's the function.
Okay.
So yeah, you're saying the function is either increasing. So it's better to kind of talk about those separately instead of trying to put them all together in one thing. So yeah, so the function could be increasing or decreasing, but the key is that the rate is going up, right? So that's what you were saying. Yeah. So what does it mean? It means that the partial with respect to x is greater than 0, which means that the partial with respect to x is increasing. change in the partial is greater than 0, which means fx is increasing. Okay, so let's watch that. Ready? So this is what this looks like. So we're just looking at z and x, right? We're just looking at z as our dependent variable. We only care about changes in x, holding y fixed. So that means that f of x could be getting less negative, right? So that's an increasing fx, getting less negative. Or what else? More positive. So rate of change getting less negative or more positive. Watch it again. This is the partial with respect to x getting less negative as x increases, or the partial of fx getting more positive as x increases. So the resulting, the graph, so then you say the graph of z is turning up. Whether it's going down or up doesn't matter, but it's always turning up. And that's what concave up means. It means that your derivative is getting less negative or more positive. Okay? Now, what about fx is less than 0? What can you conclude about changes? That means changes in the partial derivative are less than 0. And if changes in the first partial with respect to x are less than 0, then we can say that the first partial is decreasing, right? Well, this is the rate of change is decreasing. The rate of change is decreasing. That's what it means for the second partial to be less than 0. So what are the two possibilities for that? F of x is decreasing means getting, right, so less positive is first. This is the partial derivative getting less positive, right? Or partial derivatives getting more negative. So as a result, a graph representation turns down. It's always turning down. If the rate of change is getting less positive or more negative, the graph is turning down, and that's how we get concave down. So this is pretty much the same, since we're isolating the other variable. If we're talking about x, we're isolating y, and then we're just talking. It's basically calc 1 again, right? And then, or we isolate x, or we isolate y and fix x. Well, it's just calc 1. So we're just for the same problem now. We just have twice as much to do, right? We just got to do the x and the y, but it's the same thing as calc 1. But I do want to make sure it's not just all about the shape of the graph, concave up and concave down, but that you're thinking about rate of change, how this affects the rate of change. So let's practice here. So now let's go back to this example here. So we'll start with the same example we had last time. So let's talk about the second partial with respect to x and the second partial with respect to y. So can we make any conclusions about those at the red point? So again, we're asking about the rate of change with respect to x. What is it doing? So we know the function is going down. So the first derivative is negative. What about the second derivative with respect to x? Or fxx. So what could help is I could turn on if I turn on a plane that shows you the fixed value of y, that might help. So what about the second partial with respect to x? Helpful? Think it's negative? Rates are decreasing. Rates are the function value is getting negative, but the rate is getting more negative. So concave down, negative. What about fixing x and looking at partial respect to y? That one's easier to see. FYY, conclusion? Also negative. See that? Rates are getting less positive. That means FYY is negative. Okay, another example. One 14.48. 2.78. All right, also all four. You're going to analyze partial respect to x, partial respect to y. And the second partials. Shoot. Oh, there we go. So I don't know if it's spinning too fast or if that spinning doesn't help, but do your best here to talk through these. Talk through these four. What can you say about these four? See if that helps a little bit.
Increasing, but FYY is also
So first of all, this plane, does it help you with the x partials or the y partials? X. Okay, so what about fx? That should be easy. Negative, because values of z are decreasing, right? Values of z are decreasing. What about fxx? So I was going for something here. Maybe I didn't do it perfectly, but what was I going for? Can you see what I was going for? I was going for 0. So maybe 0 is more back here? Yeah. Okay. So what? Y a little bit, x a little bit less? Try that. Does that look more like 0? Yeah. So I was going for 0, meaning that for a moment there, right? So the rate back here, but the rate is doing what? Decreasing, and then somewhere it starts and turns to increasing. So somewhere along here, I think I'm pretty close, is where the second derivative is 0, because the rate is changing from decreasing to increasing. And so there, right there at that point, there's going to be a moment when the second derivative is 0. the rate's neither increasing nor decreasing. Good on x? Okay. Turn that off. This on. All right, so take another second to talk about y. What that do? Okay, how about Fy? Fy, the first partial with respect to y? Pretty close to 0. We're kind of in the y direction. We're hitting a low. So in the x direction, it's cruising down, but in the y direction, we're kind of hitting a low spot. So f partial with respect to y is pretty close to 0. Fyy. Someone has offered up positive. Yeah, even so, to the left of it, the rate is becoming what? Less negative, and then to the right, more positive. So it's not just because the first derivative is 0 doesn't mean the second derivative is 0. So all through there, even at the bottom, the rate is increasing. Even at the bottom, the rate's, because it's getting less negative, and the rate's getting more positive. So all through there, we got a partial respect to, the second partial respect to y is positive. The first partial respect to y is 0. We're at the low point. Questions on those? Okay. 13.2. Oh, that's the one we just did. Okay, so 170.8 and 17. Off. And 1.72. Okay, go.
Is Fy increasing or just?
Okay, what am I helping you with this plane? How am I helping you with this plane? Y, right? I'm holding x constant. So the first partial with respect to y is 0. Topping out, right? So it's for a change in y, you don't have a change in z. For a small change in y, right? So that's 0. For second partial with respect to y? Yep, the rate is decreasing, getting less positive and more negative. Rate's decreasing. So second partial with respect to y is negative. Okay? With with respect to x, first partial is negative. Second partial with respect to x, negative. Both negative, right? Heading down, getting more bigger negative rate of change. So negative and negative. Question on that? I think I want to decrease right here. Okay, special point. What's going on here? Both partials, first partials are 0. And what do we have then? Local maximum, right? So this is local maximum. In both directions, partial with respect to x is 0. Both partials with respect to the second partials are negative. In both direction, rate is going down, right? Rate is getting less positive and more negative. Okay, so this is where we're gonna talk about critical points. So when both the first partial derivatives are equal to 0, then what could you have? Local max or local min, right? Okay, go. Why do you increase and x to decrease?
I think that's FX out.
Is that better? Okay, I think I got it. Maybe I need to do it again here. Shoot. Maybe do I have it now? Or do we go too far?
Oh yeah.
Is that better? You know where I'm going for, right? All right, what about the first partials here? Both zeros. Is this a local max or a local min? Really, it's a local min?
You look at it like that.
Both, right? Is it a max? Oh, it's a max. Oh, wait, it's a min. It's both. Okay, this is, so it's not, if your first partials are both 0, you're not guaranteed a local max or local min. Here's the case, and this is called, giddy up. It's called a saddle point. It's called a saddle point. So in one direction, or multiple, it could be multiple directions. You have a maximum. Like if you head in that direction, you'd always go down. But then in at least one other direction, if you take a step, you go up. So that's a saddle point. So an easy way to draw those, if you're just trying to go like this, and then this. So right there, go left and right on the page. Fix that a little bit. There we go. All right, so then right at that point, if you go kind of left or right on the page, what? That's a minimum in that direction. But if you go kind of forward and back, you got a maximum in that direction. And that's the same thing we have here on the graph that I showed you. It's called a saddle point. So having a partial derivative, both partial derivatives equal to 0 does not guarantee a local max or min. So certainly at local max and min that is true, but just because you have both partial derivatives equal to 0, it doesn't guarantee a local max or min. You could have these things called saddle points. Okay. Do you see it? Does it make sense? Okay, so just as practice here. So I want you to count, I'm going to show you a graph. I want you to count how many local mins, local maxes, and saddle points.
Oh my god.
Ready?
No.
Of course not. Okay. That's a pretty cool graph, huh? We're gonna actually in a couple weeks we'll do a problem dealing with this function. If you know your calculus, it won't be so bad. Okay, so let's talk about these critical points. Critical points. Okay, a critical point is of a function z equals f of xy is any ab such that the first partial derivatives are both 0. That's what we mean by a critical point. So as we've seen, if you have that case, you could have a local max, a local min, or a saddle point. So once you have an ordered pair that is a critical point, you calculate this thing called the discriminant. The discriminant then will help you determine which one of those three you have. So here's the discriminant. You multiply the second partials fxx times fyy, and you subtract the product of the other two, the fxy and fyx. But there was something that showed up in the homework. Chloros Theorem says that those are equal. It's a theorem that if you do the partial of first with respect to x, then y, you get the same function as if you did y first and then x. So since those are equal, you could just pick one of them and square it, because they're the same. So normally you just do fxy and square that, so you don't have to do it twice, because you're going to get the same thing anyway. Make sense? So that's what we're going to calculate for each ordered pair AB that makes the first derivatives equal to 0. Right? So this makes sense that it has everything to do with second derivatives, right? That's just like Calc 1. When you had a critical point, to find the test for what your critical point was based on the second derivative, right? So this is complicated. We got two different independent variables. So now we have this complicated formula based on second derivatives that help us tell us what kind of critical point we have. So here's what we do. So if that thing is greater than 0, if your discriminant is greater than 0, you don't have a saddle. It's going to be a local max or min. And so now, how are you going to find out if it's a max or min? So I asked that question to you. So the discriminant is not going to tell you whether it's local max or min. We need something else. So what can we do to figure out?
Use the whether fxy is greater than or equal to 0.
Which one?
Either of the. Never mind.
No, I think it might have been right. I just maybe didn't hear it. Yeah.
So if f(x) or fyy, if they're both positive, that means it's a local minimum.
Yeah. Is that what you said?
I was talking about the other one.
Yeah. So if we know for sure it's a local max or min, then all we need to do is look at these. Right? If fxx, is this what we're going to say, Harrison? If fxx and fyy, what is greater than 0, then what do we have? That means the rate is increasing, getting less negative or more positive. Minimum, So now you're just like Calc 1 again. You the second derivative test. You're going to look at these in particular, and if fxx and fyy are negative, rate is getting less positive, more negative. You've got a max. So once you get d is greater than 0, then you just do the standard second derivative test from Calc 1, looking at these two. And then determine if you've got max or min. Does that make sense? Okay, if d is less than 0, saddle point, and you're done. Right? So if d is less than 0, you've got a saddle point, you're all done. If d equals 0, then there's no conclusion. So you'd have to figure it out some other way. So it's something, it's a critical point, it's one of the three, but for whatever reason, the discriminant is not giving the information there. So again, same thing. Max is when the second derivative is what, positive or negative? Second derivative is negative. Min. The rate is increasing or decreasing? Rates are increasing. Second derivative positive. This one you can count. So how many local max, local min, and saddle points? How many local max, local min, and saddle points? That's a reasonable question. Go for it. Talk about that.
It's like 2 sides.
Yeah.
So why wouldn't we just look at the sign of the second derivative? Like if they're like different signs, then wouldn't that just be saddle point?
Yeah, let's see. Yeah, but that doesn't guarantee a saddle. That's not the only case for your saddle point. You could have both second derivatives being positive and still have a saddle point. Because you could have like a bunch of different maxes in different directions and mins in different directions. So like imagine like at that saddle point, it went up and down and up and down and up and down all around. So in the x and y direction, you could have minimum. But in other directions, in between, you could have maximums. So it's not enough. So that is, yeah. Okay, how many local maxes? Just looks like there's one. How about local mins? 1. Saddle points? 2. Okay, so we're going to chase out the math here. We got 8 minutes. And we want to confirm that. And then actually find these critical points and the values of z at those critical points. So here's the math. So this is the function. So let's do the math and confirm what we're seeing with our eyes, okay? So what do we need to do? To find critical points we're interested in. What makes a critical point? Not the second derivative. First derivative is 0. So we're going to find those first partials. I'm going to do it fast. 6xy plus 0 minus 6x. There's my partial with respect to x. Partial with respect to y. (3x squared) plus 3y squared minus 6y. Okay? And so as you're solving this algebra, you just got to keep telling yourself, I'm looking for all ordered pairs that make both of those 0. That will guide how you do the math, how you do the algebra. I'm looking for all ordered pairs that make both of those equal to 0. All ordered pairs that make both of those equal to 0. So I'm going to first start by saying 6xy minus 6x equals 0. And 3x squared plus 3y squared, 6y equals 0. So depends on the problem. The approach that you use is different, but factoring is really helpful. So which of those two factor? The first one, we can pull out 6x, and this is very helpful. Because that tells us that in order to get that second partial, or the first partial with respect to x0, two things has to be true. Either x has to be 0 or y has to be 1. So we'll say x equals 0 and then find out what y could be with the other one, right? To make it 0. So first x equals 0. That means that if x is 0, that means that 3y squared minus 6y equals 0, and that factors now. Pull out 3y. So we get y minus, again, we need all ordered pairs that make both of those equations equal to 0. So what did we just find? 0, comma 0 or 0, 2. Both those ordered pairs will make both equations 0. But then, from that first one, we also said that what x could, or y could be 1. Going back to the first equation, if y equals 1, then we have 3x squared equals, or 3x squared plus 3 minus 6, which means 3x squared equals 3, and x could be plus or minus 1. All ordered pairs that make both equations equal to 0. What did we just find? 1, 1, and negative 1, 1. Okay, did I lose anybody? Are we in agreement with what our eyes are seeing so far? 4 things, right? We said a local max, a local min, 2 saddles. We got 4 critical points. Okay, so with these problems, there's location and value, right? So are these telling us location or values of the critical points? Location or value? This is location, right? X and Y. Values of the independent variable are telling us location, right? Location. And then now if I want to know the value of the absolute max or min, that's a matter of what? Finding the z values, right? So we'll go ahead and find the z values. Find all the z values associated with these. Oh, so no, we got to do the discriminant. What am I saying? We got to do the discriminant, second derivatives. So what's the discriminant? So we're going to determine what is what, right? We're not going to rely on the picture at all. The picture confirms it, but we're going to do the discriminant. So that's what? fxx y minus fxy squared. So what's helpful with these is to make a table. List out your critical points. And if you make a table, then once you finish the table, you can just make your conclusions. You'll have all the information you need in the table, and you can make your conclusions. So that means we have to find fxx and we have to find all these. What is fxx? 6y minus 6, is that right? Fyy? 6y minus 6 again, is that right? Happens to be the same. That's just a coincidence. That's not necessarily the case. And then fxy. Just 6x? So again, did I do the math right? That's peculiar. It's just because of the symmetry of this function that those turn out to be the same. Normally they won't. So at 0, 0, what is fxx at 0, 0? Negative 6, fyy, negative 6, fxy, 0. Discriminant is 36. 0, 2, that's 6. 0, 2, 6, fxy, 0. Conclusion, positive 36. 1, 1. Negative 6, and 6 makes 0. What's one of those is 0? Negative 36. Finally, negative 1, 1. That's still negative 36. Minus negative 6 squared, still negative.
The first one should be negative 12.
Yeah.
I'm not very good at math. What is it? These are negative 12?
First one.
You plug in the y value, which is positive. Oh, yeah, you're right.
Oh, yeah, I'm an idiot.
Is that right?
I'm bad.
Yeah. We're bad.
Okay, conclusions. So this could be max or min. How do we know if it's max or min? Look at the second partials, right? Second partials are negative, so this is max. Max or min, therefore, second partials are positive. Min. Settles. Okay, and then finding the values of the max and min. Just a matter of plugging your critical points into the function, getting the z values. So if you want to know at what's the height at the local max, plug in your 0, 0 into the function. What do you get? 2. So that the value of the local max is 2, because it's what you get when you plug 0, 0 into the function. Okay, I'll change the web work should be 7, not 5 p.m. That's for the linearization and differentials. This will be Wednesday, 7 o'clock.